A very good afternoon to all of you. I'm Ankita Chauhan from NASSCOM's Product Council. I'm back with another interesting episode of our data science series. Your feedbacks convey how interesting and enriching these webinars have turned out to be. Almost all sessions are a full house now. Without taking much time, let me introduce you with our today's speaker. I have with me Dr. Manish Gupta, who is Vice President, Machine Learning and Data Science Research, Head of Risk COE in American Express. He is proficient in building innovative and disruptive solutions for business insight using huge amounts of structured and unstructured data using cutting-edge machine learning, data mining, big data, deep learning, and text mining technologies. I'm sure today will be a very insightful session. Before handing the steering to Manish, I want to tell you two things. Number one, you can write your questions anytime during the session. Manish will answer most of them after his presentation. Number two, please fill the feedback form at the end to help us improve our future webinars. Over to you, Manish.
Hi, thanks, Ankita, and welcome to all of you guys for this deep learning session today. Just quick brief about that. I'm interesting to see that 15 years back, once I started building my first neural network models, that time the deep learning term was not coined, and now people are talking about deep learning AI a lot. So I probably try to start this session with a joke, which some of you might have already seen it, which essentially talking about different perception about the deep learning in the society, in the friend circles, and how the people think. I think you could correlate the deep learning guys, whether they might be sitting on or lying on a bunch of wealth that you could see in the third picture out there. But at the same time, we believe that we are developing algorithm, but essentially most of the time we try to do kind of coding to build an experiment, various deep learning experiments for our use cases. And if I'll go back to the outline of this talk, I try to cover these 5 broader ideas because I know that I may not able to cover and do justice to the deep learning topic in 1 hour. But what I'll do here, try to cover these 5 basic areas which may pertaining to the deep learning side of it, and give you at the end some key takeaway. So these 5 key questions comes up in any topic. Why a particular topic? So that's why the why deep learning. Why essentially now? Why it is becoming popular today? What is difference between machine learning and deep learning? So there are few things I'll try to cover into this why deep learning is relevant for us today. And then the second question is that, okay, I know about why it is required, but which are the popular deep learning algorithms? There are a bunch of people are talking about various set of algorithms, about what exactly these algorithms are. I may not able to cover all of them, but I try to cover at least one, so that you will feel a sense about how these deep learning algorithms works, what are the basic training process, how essentially we build. Then third question comes up in everybody's mind. Okay, I know about deep learning, I know about deep learning algorithms, but how to choose a deep learning algorithm for my use case? Because there are so many algorithms are out there. Which one suits to me? Can I have kind of guidelines which can help me to really select a particular algorithm for my use case instead of investing a lot of time and energy for experimenting in all of those algorithms? So that's why the third topic is more talk about how to choose a deep learning algorithms. And the fourth is like, okay, I know which algorithm I need to work upon. Can I build this one? How to build a deep learning models? I try to give you some snapshot code view how exactly the deep learning algorithms built using various deep learning frameworks like TensorFlow and Keras. And at this end, I also want to give you some kind of a tips to build an efficient deep learning models, because people may fail a lot while they're using the deep learning models, because they need to fine tune those parameters in a right way in order to get the desired results. That's why I'll give you at the end some tips as well, so that. And since this talk may not able to cover within 1 hour all the deep learning topics, I want to give you where to learn more on deep learning, because there are a bunch of links and notes out there which are best suited for me, or which particular algorithm where to read. I'll give you a few references. I'll probably may walk you through some of the references which may be helpful for you to take the deep learning journey as you go forward. I think I'll start this slide, which will tell you some kind of a set the agenda out here, which essentially lot of people get confused between AI, machine learning, and deep learning. Essentially, these are all integrated. I would say AI is a bigger term. Even before 1950s, people are like robots and all those things were there. I worked in DRDO also. In 1950s around, people started using various machine learning kind of concept out there for warfare and all, but they were not that popular and not called like an artificial intelligence, but these things were there. In fact, all of us have seen those movies like Terminator and all. They are being coming from those kind of theories and concepts there only. Now the things started like machine learning, which again able to start flourishing it. In fact, once I started my PhD 15 years back in the area of machine learning from IIT Delhi, that time like hardly anybody knows about machine learning as a topic. Even first network model which I built in 2003, I was even having no clue around that time. Now the deep learning is obviously giving a lot of breakthrough and driving this AI boom as we go forward. So there are various reasons for that too as well. Now the first question comes up: why deep learning? Why not simple machine learning? Why not the traditional algorithms? And why now it is? Um, so I think the major driver for this is the amount of the data. As we increase, the machine learning techniques used to saturate at a given point of time, and the performance basically saturate very early. If you talk about the algorithms of machine learning, popular algorithms, let's say the SVM or the logistic regressions, things of that nature, they saturate very fast. Even if you give the larger amount of the data, they may not able to make more out of it. Uh, so that is the thing. But as you start building your shallow neural network to the deep neural network, you see that as you keep adding the data, the performance keep improving upon. That is one of the major factor of driving the deep learning research, because the lot of availability of the large training data is started available to us. Basis the storage cost is getting cheaper day by day, as well as we have now GPU computing, which can able to run those complex algorithms in a no time. In fact, not only GPU, we have things like DGX box of NVIDIA, which is kind of a distributed GPU computing as well. And obviously, in last decades onwards, there are a lot of algorithm advancement also start happening on the deep learning side, which are further given the boost to the deep learning. So essentially, it's more about availability of the data, which where these algorithms can work upon better and keep giving you performance benefit. That's what we also see. Now the another question comes up in people's mind is why deep learning versus machine learning. So there is the major difference between deep learning and machine learning is that machine learning, we require some kind of feature extraction mechanisms before classifying an object. Let's say earlier we used to have an image classification where we used to create features like shift, SOG, those kind of features, even ICA kind of features. Sometimes PCA also people try to use it. Color histogram, those kind of features used to create it, and then a classifier algorithm used to work to decide whether an output yes or no. But with the advancement of these deep learning models, especially the algorithms like CNN, which is convolutional neural network, I'll touch upon that basis. You don't need low-level features now. The algorithm is still being written in such a way that it extracts those features by itself as well as classify those objects in a go itself. So essentially, if you see for a deep learning, there is no need to feature design, especially in the area of unstructured like images, speech, text, things like that. But and now the deep learning algorithms can work on a sequential data, like time series kind of data. The algorithms like LSTM, GRU, or the basic RNN algorithms works very well on the sequential data. At the same time, but the one of the limitation the deep learning is that the features are not easily explainable, because the way the human works also, it's not easy, the some of the rationale behind for some of our decision making. Sometimes the algorithms are in such a complex, it's difficult to explain those features what are being getting derived, but still the research being happening, especially the area of the CNN, you are still able to get what kind of features can be extracted, but the area in the RNN space is very difficult to get it. Obviously, machine learning itself is a preferred choice for structured data. even majority of our being a part of the American Express right now, we also leverage a lot of machine learning algorithms in order to decide uh, whether it's an event is fraud or not, whether there is a credit default would happen or not. And these are kind of billion-dollar problems, I would say, which we try to address through machine learning. And now moving on, now moving on to the second question, which is again in my mind is very critical questions. Which are the popular deep learning algorithms? I'll spend some time on this particular slide in order to really tell you about, although this list is not exhaustive here, but try to cover the major area of the deep learning algorithms. If you see the leftmost is the deep neural networks. Basically, it is also called multi-layer perceptor model. But earlier versions of the machine multi-layer perceptor model is were having only a few layers, and that's why they are called shallow networks. Because if you have more and more hidden layers, let's say now people talk about 50 hundreds of kind of hidden layers also for those deep neural networks, depending upon the nature of the data and the problem you're trying to solve. But people are interchangeably use deep neural network as well as multi-layer perceptor model. In fact, there was an interesting story I'll let you know about. Um, in 1960s, around the first neural network model came up, which is called Perceptron model, also called single-layer perceptor model. And then Minsky and papers, there is other scientist, they have written a book to just criticizing about the neutron model itself, that is a single layer perceptor model, and that they criticize so much that 20 years in the history of the network there were no research, like 60 to 80 there were no research, and they criticized that XOR problem they were not able to solve it. And the moment the first multi-layer perceptor model comes up which can address the non-linearity also, then further research start uh, going into the network area. So the main the network actually dies many times as well as comes up many times. Now it's going very rapid pace, and the thing is called deep learning here. So the major application for this deep network is like the moment you have a structured data, it's a pretty much useful. In fact, all the whether you use CNN or RN kind of algorithm, the last layer, which is your flat layers, they are essentially the multi-layer perceptor model, which is essentially the feed-forward network at the end, which you called the last layer for decision making. So essentially, the classification forecasting is something or the popular application of the first algorithm, which is called a deep network. The second popular algorithm, which is also called convolutional neural network, which is CNN. Again, Likon and around early 2000, they came up with the idea of convolution network, and this essentially revolutionized the whole image recognition industry. And in fact, I have a slide about that, how the efficient this particular algorithm is. In fact, I'll go more in detail this algorithm for today's talk and try to brief you more on those lines. The second, and essentially this is, as I mentioned, this particular network, which will go into the detail, talk about the feature extraction classification images, and very popular in the area of object recognition, and image recognition area. The the third algorithm, which is again a very popular and one of my favorite algorithm, is the recurrent neural network, which is also called RNN, and they have various variants also, LSTM, which is long short-term memory, as well as GRU algorithms. And this algorithm is very popular in the NLP space. Those who are working into the NLP side and text processing side, there's no brainer. You just simply use this algorithm, and it's a magic actually. You'll see this algorithms works very well on the time series data or sequence of events. In fact, we also started leveraging this algorithm at our own for risk management side, and it is giving a lot of gain to us. Um, and I also want to, although I'm not able to cover this RNN today, but it's again, I'll leave some of the references to you guys so that you could later on walk through this RNN topic, and which is very interesting actually. And I also wanted to touch upon three measure algorithms also, so that you know that there are different varieties of algorithms also exist, not only just these three. The another set of algorithm which is called autoencoder, which is essentially unsupervised algorithm, and the basis the construction and reconstruction losses, they actually try to learn out of the images, and for various other feature engineering purposes that it being used, because people sometimes may get confused. The deep learning can be used only with the label, but this particular algorithm can work on as an unsupervised fashion, and it's very much being used for uh, outlier detections as well as anomaly detections, as well as feature engineering. So that is pretty popular. In fact, there's something called variational autoencoder, which is again a popular algorithm in that space. The another area of the algorithm of the deep learning is called GAN, which is called General Adversarial Networks. This particular algorithm is like revolutionizing the industry. In fact, this particular algorithms being used for data synthesis, data augmentation, because we have because deep learning requires lot of uh, data in order to predict better, and sometimes we do not have that through those labeled data or those kind of variety of the data, and these particular algorithms help us to generate millions of data points by understanding the distributions of few samples and create more samples around those lines, and can generalize the model better. So this particular algorithm is essentially a data augmentation algorithm, which can really synthesize the data and create some artificial samples for a given data. And it is very much in use. In fact, this algorithm also been started getting used for missing value imputation, because we have come across many applications where the missing value rate is very high, especially in many industry. The missing rate is very high, and this particular algorithms coming up as a panacea for solving that kind of problem also. I think you might have heard of the reinforcement learning, although this is another kind of learning which basically learn a policy making by incremental learning ability, like the way as a human being we learn bicycle. There are various games that we play. This particular reinforcement learning algorithms is also getting very popular. I'm not able to touch upon all of them, but I just wanted to give you a heads up about these algorithms. Now, I think to give you some flavor about how the image recognition examples looks like, you could see that for image recognition, the first three pictures are, we can easily say that they are probably a sunset pictures easily. But we need to really train a computer to really say that these pictures belongs to the sunset. And as a human being, we could easily say that these all belongs to A, or handwritten characters. We can easily really make use of it. But it's easy to label them, but difficult to explain. That is the same problem the industry is facing: explainability of the deep learning models. In fact, that is another key area that we are working upon: how to explain these deep learning models. Same case with the example of speech recognition example. Even if we speak the same words, different speaker may have a different pitch, different pauses, different tone, and they may have a different signals for the computer to really understand. And that's why it's not easy for a computer to really learn those speech signals. Now let me give you a few slides about those algorithms, this at least to one MLP, because MLP is anyway is an essential part of any of the deep learning models, especially CNN and RNN, which is the last layer. And this MLP, essentially there are three major layers. One is the input layer, where you feed your data in the input, and then they pass it on these networks to the hidden layer, and at the end the output layer, whether you wanted to do prediction or the classification, it depends upon that. But you could create multiple hidden layers also, and at the same time the few parameters needs to get trained. Like the parameters could be the depth of the network, means how many layers you wanted to create uh, in your network. The width of the layers means how many neurons you wanted to add. Let's say if you have uh, only three variables, so whether you want 300 neurons in your hidden layers, whether you want only 5, whether you want 10, so these parameters also need to get trained. The epochs is something like where you pass through the whole data once. Uh, that is called one epoch. If you pass multiple times this data to the network, that called multiple epochs. So you need to really fix upfront that how many epochs you wanted to run for your training out there. The batch size is something that for every batch, let's say you take a sample of your data and then update the weights after that batch get processed. That's why the batch size is very important. I have some tips around that, how to really figure it out, batch versus epochs in a given training cycle. The learning rate is essentially very important. What rate you wanted to learn your networks, whether you wanted to reach very fast, whether you wanted to reach very slow. Let's take an example. Suppose you wanted to go to Delhi to Mumbai by train. You know the distance could be around 1600 kilometer. Uh, but first few hours you will see there is hardly any stoppage in the train. It means the learning rate could be very high. But as you reach to the destination, your speed may get slow. You may have more frequent stations, so your learning rate could be low. So that is essentially the game here. In fact, sometimes people use the cyclic learning rate also, which is very effective, which is nothing but a sinusoidal graph of your learning rate, and which can help you to really reduce your dependency or to fix or fine tune your learning rate, and that works very well. And dropout rate, which is again a very popular feature of regularization. If you know about overfitting of networks, then actually neural network models overfit overfit very easily. So you need to really use some kind of regularization which can address those overfitting. And dropout is something, one of the regularization parameter, which basically switch off some of the neurons in the learning part during the training side time. So it means they do not take uh, uh, participate in the learning for some of the uh, update once the training is happening it. So that's the dropout. So how many neurons you wanted to switch off in your network for a given training cycle, that is called dropout rate. Activation function, which is essentially a very important uh, input, now it's getting standardized in terms of people start using the ReLU, which is nothing but either zero or the actual value, or it takes the maximum of that, which essentially tell you, which basically kind of a limit or normalize your output and activate into a certain limit. We have a various activation function like sigmoid, 10, hyperbolic, linear activation function also sometimes people refer it. But the major thing is on the uh, let's say ReLU is becoming a popular, and which layers you should use which activation function. I have some tips around that line also, I'll share with you. Now coming to this particular algorithm, which I think I can go bit on detail, which is called CNN, convolutional network one. It essentially have um, um, three major layers. One is called convolution layer, which is again convolution and activation put together. And there's a layer called pooling layer, which again people try to subsample your image to the pooling layer. I'll give some detail around those line. And then at the end you flatten your networks, and then fully connected layers you basically pass on to the uh, MLP basically at the end. And although I'm not going into the details of the mathematics, but there's very interesting reference which I quoted in the slide at the down, which is Andres Karpathy's. Basically, it's a Stanford course, and he has a very interesting notes on that particular CNN one. I strongly recommend you guys go through if you really want to understand the some of the mathematics behind this algorithm. But essentially, if you talk about the images, even as a human being, what we try to learn, we try to create some low level features first. Let's say if you wanted to recognize a face, what you first try to learn, whether you wanted to learn features like how the nose look like, how the eyes looks like, how the color of the skin looks like, and how the hair looks like, and these kind of features you create in your mind, and basis that you classify whether it's uh, a man or a woman. or maybe Indian versus Chinese, those kind of thing. Because if you have to classify between Indian versus Chinese, you may see that they have a small eyes, we may have a bigger one, they have a different complexion, we may have different. So these kind of features essentially get extracted during the training phase itself. And I think let me go through some of the intuition more. Although we see as an image, but computer see as those numbers only. So that's what the computer sees. Now the computer needs to really make these numbers into account in such a way that any incoming image, they should be able to really tell that whether it's a bird or a cat or a dog. So that's why the CN networks try to find patterns in these numbers of classifications. And how they do. Let's say uh, I am wanted to create a CNN model for this particular bird image, whether it's a bird or not. What essentially I want to first uh, learn from this image. I want a smaller patterns from the whole image. Let's say first I may want it to have a beak detector. Let's say, and I'll tell you about how these beak detectors can be used as a filter and how they slide through that way as well. So in order to create this particular one, I probably may need a beat detector to create a low level features. If there's a beat peak out there, then the chances there is a bird out there. So I probably may need to have a filter which can detect the beak from an image, and that may tell me about whether there is a bird or not. So these kind of features get created. And think about an image or those filters like as an analogy, you could consider these are the uh, lenses or torch which you are scanning through over the images, and given torch at a given time is lighting only one set of the image and reading from that, and then is slowly covering the whole images, and that is called striding, so that they can cover the whole images. Similarly, you may need different kind of features also. For example, this beak can be at different places. Then in that case, you need to stride through these beak detectors. Some, or maybe you need a different filters for this. One could be let's say upper left beak detector as a filter. One could be middle beak detector out there, and these type of filters, that's why you need for a convolution layer you need different kind of filters, because these filters may tell you about different kind of features of a given image. And then later you wanted to compress. So the convolution is a layer essentially is nothing but you are having a filter which you are scanning through over the whole images, and these images, then obviously it's kind of a dot product at the end you are taking, and some value out of it, it is you are taking it out. Then you create a number of filters that does convolution operation over an image and pass it into the output layer, although it's going output, but essentially there is some further layers in between. Let's say the one layer could be the ReLU layer, which is essentially the activation layer, which can basically normalize some of the patterns. Some, because some values may go negative, they may limit to the zero, and some exact value it can take it up. And once you have that image coming from the convolution layer, you may go for pooling. Again, pooling is nothing but and it is very essential also. Subsampling pixel will not change the object. For example, whether you have a large bird image, whether you have a small bird image, it doesn't really matter too much for this. And but at the end, it may help you to save the computation time, as well as training the less number of parameters in the training period. So we can subsample the pixels to make the image smaller by using the pooling, and maximum pooling is something that people prefer to use it uh, in the given one. Then that's what the few parameters to characterize the image. Now essentially if you look at the architecture now, you have a image, you have a convolution, you may have a max pooling, you again can go for convolution, you can go max pooling, and you could repeat these uh, process multiple times. And this particular repetitions, like even if you talk about the famous networks, like AlexNet and all, they have a 152 layers, or these type of networks are coming it up, and then you finally put into the fully connected networks at the end, and that the output layer will decide whether bird or not. So I try to give you very high level of CNN architecture, but essentially it's creating a low level feature from the images, passing on to the fully connected feed forward networks, and that at the end will decide whether there is a bird, cat, or dog out there or not. Now, um, I'm not getting into the detail, but I've given you the link which can tell you about the uh, mathematics of that one. Although there are a few more references in the papers which you can read through. Now, the third question comes up with how to choose deep learning algorithms for my use case. So there are various use cases exist in the industry. The one of the most popular one is like the basic classification, whether it's a sunny day or a rainy day, or whether it's a default or a not a default, or whether it's a patient would come to us or not to come to us, people will respond or not respond to a product or a campaign. So the all bunch of those kind of problems comes into this deep network framework, and the moment you have more data, you could create more feature. I'll give one examples from my one of my previous work. We used to build uh, Jeevan Sati uh, uh, propensity models, which essentially being used for reaching out to the customer whether they're likely to subscribe to us or not. And the kind of features that jeevansati.com, you might have heard of this one. And the feature we used to create basis the profile as well as behavior information and how likely they are to respond to us. To give an example, let's say I want to create a marriageable age as a feature, but uh, the it could be different for boys and girls. It could be different for a different community. Uh, then I need a different kind of interaction among those one to create a features around that line, and then build that kind of models, propensity models. And there the deep network is very much popular. The image recognition and object recognition, there's uh, no brainer. You could just simply use CNN, that would work. um, that can easily be do. The speech recognition, time series, NLP, these are popular application of the RNN, which is and most of the time you start using the LSTM itself, which are very popular in the industry. Uh, and you may talk about any of the use cases. I think you may fit three of them. Or if you do not have a labels, then I would say that the variational autoencoder is one of the algorithm which you could use it. Now, the other industry applications in finance, like fraud detection I mentioned, even manufacturing anomaly detection is also one of the one. CNN for video analysis, also for measure the traffic, for satellite images, for automobile, for healthcare. In fact, uh, a couple of weeks back, I was in KDD conference, which is knowledge discovery and data mining conference, which is one of the topmost conference in data science. Uh, happened like this time it happened in London. In fact, there was a full day workshop on healthcare, deep learning in healthcare. And healthcare is one of the area where the deep learning is prominently being used, and it's being used uh, so heavily that everything if you see out there, it is getting used. Not only just simple for radiology kind of thing, but predicting the patient visits for readmission of the patient. And there are various kind of problems in the healthcare industry, people are using it. Insurance also, for the claim severity estimations, people are using it. Neural network like various voice, NLP, chats, text, social media, real-time translations, the Google Translate, they also use it. Photo captioning, um, and finance, obviously we also start using it for our use case. Now, to give you how the MLP versus CNN in the image classification side, we ourselves ran one experiment on the MNIST data, which is a very popular data uh, for handwritten digits and commonly used in the industry. We were having 60,000 images for our training data, and each one is 28 by 28 pixels. And since they were only black and white, so essentially we have a 784 with either 0 to 255. values it can take out there. And the test data, we have taken the 10,000 examples and to detect whether it's a 0 to 9. So essentially there are 10 classes to detect those digits. And the approach for both the algorithms, you could see the difference in terms of the accuracy. One is 90%, another is 99%. So that's why it revolutionized in the image recognition. You yourself can run and see how CNN for an image recognition problem is essential or very useful and no-brainer to use it. Now, I think some of you might have heard of this ImageNet as a challenge, which is again a large-scale visual recognition challenge, and it basically shows the right-hand side few graphs actually shows just a shallow networks and top 5% classification error, and you could see the classification error went down from 25% to 16% by just using AlexNet, which is nothing but a CNN network with 8 layers, CNN algorithm with 8 layers. Now, uh, 3.57, which is a ResNet network, which has 152 layers, uh, and the human accuracy is actually 5.1 error. And now the Google net, they have released a LeNet actually version 4 in 2016 that has 3.1 uh, as an error rate also. They have further reduced that error. So this essentially is tell you about how these different networks, which are now kind of industrialized at various services. Let's say if you use SageMaker, Amazon one, they have Amazon recognition kind of services which you could leverage backend. These algorithms are running, and you could easily classify an image uh, to a problem. Now, the fourth question I want to address is how to build deep learning models. Uh, and before we go into that, if you see the right hand side, there are a lot of deep learning frameworks. And since um, the majority of the deep learning algorithms runs on the GPU because of the nature of the data and the algorithms, training time, and uh, and these basically the underlying GPU works on things like NVIDIA, their CUDA kind of libraries, but the one of the deep learning frameworks like these Keras, TensorFlows. In fact, Keras is not a deep learning framework. It's just a Uber network which basically give a high level of abstraction to the any majority of the deep learning frameworks like TensorFlow, PyTorch, Theano. Even Theano is getting obsolete. And MaxNet by Amazon, CNTK by Microsoft, Glucon I think by uh, Uber. So these networks, these frameworks basically help make your lives easy in order to train those uh, build networks. And there are four major steps in any deep learning models building. One is first you need to define your model architecture. How many layers you wanted to put up, how many neurons you wanted to put it up, how dense you wanted to create, what kind of activation function you wanted to use it. There are a lot of bunch of model parameters you could define in the beginning, and then you need to define what is your input and output for your network. And then you also need to define your loss functions. For example, if you're going for uh, a classification problem, you could use simple cross entropy kind of loss functions easily. And then you also need to define your metrics, whether you are looking for a recall, whether you are looking for a precision, whether you're looking for a accuracy. Um, so you could define your thing and then compile your network. And fourth one is you could run your network at the end. Let me give you a brief snapshot about deep network models which you could build in Keras. Um, and first of all, you need to import your those Keras modules in the Python. Obviously, once you talk about the deep learning coding and all, so people just go blindly for the Python, and because all these deep learning frameworks they have their Python support, so you could easily call those libraries from Keras.layers, Keras.models. You could import input dance models kind of things. You could create a tensor first. The first step, as I mentioned, is defining your architecture. So here I've defined um two hidden layers which is essentially 32 neurons and 8 neurons with the activation ReLU, and inputs you're passing on to the first hidden layer and the second hidden layer, the output of the first hidden layer going into the second hidden layer, and then it's further going to the output layer, which is, since we are defining only binary problem, then it's only one input output neuron, and most of the cases activation function at the end would be the sigmoid, and the intermediate activation functions are ReLU. And then you have a second step is essentially your how you're feeding the model in, then what is your input, what is your output, what you have defined in the beginning. And third step is you are defining your optimizer, which is basically there are different kind of Adam, RMS prop, those kind of optimizers you could use it. The loss which you're, as we're saying, for binary problem, cross entropy itself, binary log like, which is nothing but negative local likelihood, which you could use it. The matrix we are coming with the accuracy, and the fourth step is you are just running this one, the model.fit, which is essentially feeding your training data, your training labels, your batch size. Batch size is very important actually. I'll come to this one for any training period, and how many epochs you wanted to go to, and also at the same time you want a validation split, let's say cross validation you want to apply for this model fit, and at the end you wanted to evaluate how the accuracy is. Even you can extract the props out of your model. Even the similar code can be written in TensorFlow, which is again very easy for the MNIST dataset. Let's say if you wanted to train yourself the MNIST dataset, they are first normalizing the train and test, the and then they are going for a flattened network, which is essentially a deep network. Then dense is 502. Then ReLU being used. Dropout, they're also using it, 20% dropout. It means 20% of the neurons will get switched off during the training period. And these are randomly being selected. It's not like that only those neurons will get switched off. And then you have a activation function at the end would be softmax, and the Adam they're using it, cross entropy they're using it, and then you could fit and evaluate. Almost similar steps you're following for the TensorFlow. You could see there are only bunch of 5 to 10 lines code which you could write, and you could build your deep learning model, which is very easy to go for and using this. There's something the source which I took it from the TensorFlow tutorials. They have a bunch of examples. They have a bunch of best practices. You just go through that link of TensorFlow. You yourself can learn. Although I was mentioned about that, I wanted to give you some tips about how to build efficient deep learning models. There's no brainer you should use the regularization, because deep learning models can overfit very heavily. You need to generalize. In order to get a generalized model, you need to use regularization, whether you use L1 norm, whether you use L2 norm, whether you use dropout. But dropout is like very popular nowadays, and dropout can give you a good performance at the end. The second aspect I wanted to give you tips about, you should start with a small batch size. So there are two benefits of a small batch size. One is you could update the weights very frequently. At the same time, sometimes having a larger batch size may not able to fit into the memory of the system, and having a small batch size you could use that into the memory of the network, and they can first train faster. And at the same time, the number of epochs can be a function of your batch size. If you are having a large batch size, then the number of epochs should be also high. If you are having a small batch size, then the number of epochs should also be small, because you are updating the weights so often. The ReLU activation function should be used for intermediate layers. That's most of the time hidden, input to hidden and hidden to hidden. But for a sigmoid or softmax kind of a function, you could use it at the last layer, so that you could decide how the output, or you could limit your decision making between 0 to 1 kind of scenario where sigmoid can work. And another aspect which is transfer learning, which is very popular. In fact, we also leverage transfer learning a lot. Instead of random initialization or wait for your networks, you could uh, use a network which have been trained for a different data set, but of different problem. For example, you have trained your network for a image recognition for animals, but now you want an objects to get trained. So you probably make use the final output, which is essentially the network weights as an initialization purpose, and then build it. And for domain adaptation also, it is very popular. The transfer learning is like very helpful in order for, especially for the smaller data set. You may not have a large samples to start with, but you know there is a network being trained on the similar problem, and the fine tuning of the weights can happen on a smaller data sets. That's why the transfer learning is very popular. As I mentioned, cycling learning rate is also improves the performance, which is nothing but a sinusoidal graph of your learning rate, and your learning rate varies time to time basis in your training period. And another aspects, those who are using the distributed GPU, they should use more number of epochs as compared to the GPU, because in GPU distributed GPU training, there is a asynchronous weight updates is happening, and because of that, uh, the the same numbers of epochs may not work. If you need to get the similar performance, you probably need to run it for a bit more longer time. But since it is distributed, it can run faster. And at last, I want to give before I take for Q&A. At last, I want to give you a really good where to learn more. I want to give at least couple of minutes on this particular slide so that you know which are those references, because these are the hand curated references which I do, because some of you guys are might be aspirant for a data scientist. I thought these two links can help you. In fact, this particular first link, how to become a data scientist for free, they have a bunch of problems. They have a various interesting links, various references within that one, and you just go through that link, and if you start following that particular activity as per the link, I think it's easy. You could go in the right direction. Second, even I myself has written how to become a data scientist, and to my understanding, everyone who we should behave like a child in order to be a data scientist, because we need to be curious enough to really take up any challenge, experiment everything, and always eager to learn, quick to learn. These kind of activities a data scientist needs to take care of. So that's why, even if you can go to my blog as well. The deep learning course is very popular by Andrew Ng. These are the series of 5 deep courses out there. I've gone through that course. It's pretty interesting course which you can go through that. Even one of the interesting video by same the Andrew Ng is nut and bolts of applying deep learning. I think it will tell you how the practical aspects about deep learning, which cases you need to create more complex architecture, which cases you need to collect more data, uh, and how to address the regularizations, things of that nature. I think it's pretty popular video out there. The CNN course notes I talk you about, the Andres Kapati one, as well as there's another interesting uh, notes also there, uh, which also talk about a lot of maths behind it. The LSTM RNN, understanding LSTM, especially the Colas note, is very popular. The link on the most cited paper links, essentially the awesome deep learning papers. This particular link has most of the things which you wanted to know about deep learning. The various popular blogs you will get to know about there. The various papers about the deep learning you will get to note there. And they have been categorized basis the problem set also. So you can go through that link. The deeplearning.tv is a very simplified, very layman language. The deep learning, if you wanted to understand, you can go through that YouTube channel and you'll get to know. And deeplearning.net is again a collection of uh, various, uh, I would say, resources or materials out there on the deep learning side. And there's the further links on the there at the end. I think I'll pause here. And obviously, this is the next webinar on the 11th on the marketing plan by Raghavendra. You could go through that. And I think I should go for a question now without waiting any time. Thank you,
All right,
guys.
Manish. All right, thank you. So let's just start with the Q&A session. So first question is, what skills we can develop to transition from software development to data scientist?
Okay. Uh, So I think it's a very relevant question to many of the software development guys. I think the very first thing I would say two major pillar for a data science is one is the mathematics. If you have a quite good mathematics statistics understanding, you could learn those algorithms very fast, and you could understand the nuisance of those algorithms, understand their hypothesis around that line. And the second thing is the Python is like everywhere being used in data science. So many times we go for a Java and the other programming languages, but for data science, if you wanted to go, I think you can't really keep away yourself for the Python. The Python learning as well as mathematics, I would say these are the two major thing software developer need to really brush it up or skill about that themselves before getting into this data science area.
All right, Manish.
Okay.
The next question is, does RNN works well for network data analysis, mainly for proactive network assurance kind of solution?
I think network kind of analysis, there are separate set of algorithms. I'm not sure this network kind of analysis RNN can handle very well, but there's something called tree RNN, which try to address some of the network related problems through the RNN way. The standalone plain vanilla version of RNN, I doubt it can do that one on the network analysis side, but there are a lot of graph based algorithms available in the research area and community. In fact, this is the major area in the KDD side. The graph based research were happening a lot, and I think if you go wanted to really understand your solution or algorithm for your domain, I would suggest go to the KDD 2018 website. There are a bunch of papers around those lines. You could go through that and maybe that. RNN directly may, I doubt, like even I'm not aware, maybe directly applicable to that problem.
All right. Now, Ankit has a question for you, Manish. He's asking, why is fully connected networks important for CNNs?
Okay, see at the end you want it. See the convolution layers and pooling layers basically help you drive the features or extract the features. But at the end you want it to make a decision whether there is a bird, yes or no, whether it's a cat or a dog. That kind of classification, decision making, you need uh, some kind of a network which can help you to do that. So CNN, where the CNN, the first few layers are essentially extracting the features, but last layer is essentially the decision making. So for any of the networks, the last layer should be the decision making one, so that you could make a you could fine tune your weights accordingly, basis the error get back propagated later. So that's why it is very much essential for decision making one.
All right. There's one question by Amita. She's asking, over the years, it's AI, ML, and now DL. What is next in future after deep learning? Quite interesting.
Okay, see, I see. Uh, People may coin a different term, I would say, in future. Essentially, the work is probably going to be the same. We wanted to predict the future, and we wanted to be as smart as human. Um, so I would say that the term may change, but the objective would remain same. So I can't really comment what could be the term for the next decade, but I would definitely sure about that. The deep learning AI would be there for the future. Whether with the different terms or not, I can't comment right now.
All right, Manish. Well answered. The next question is, shall we use Jupyter or Spider? Can you explain what is the drawback of using Spider in space of Jupyter?
Okay, I doubt these both you could use it. There's hardly any drawback. It's more about how much environment. Both are a kind of a notebook kind of environment, and I prefer to use Jupyter a lot. It depends upon someone's hands-on to a particular environment, and both can do the same job. I do not see too much difference between them. But if you are a beginner, I would suggest go for a Jupyter.
Okay. So the next question is, I am very naive to machine learning. Can I directly learn deep learning techniques? Will it be tough for me to adapt, or can I learn with ease? A question by Vamshi.
I think there is not too much prerequisite that you need to learn machine learning before learning the deep learning. I think it's more about your interest level uh, and understanding some of the mathematics behind those deep learning algorithms. You can directly jump into the deep learning. It's not to, because some of the machine learning algorithm does not have any saying to the deep learning. Let's say SVM kind of algorithms, which used to be one of the time very popular algorithm. Now it's not there for the deep learning setup. You needed to learn those kind of algorithms, but the basic understanding of the classification, basic understanding of the machine learning jobs helps you to really comprehend the deep learning problems better, and what kind of features would be relevant for you to really do the classification or prediction kind of job. uh, that would help, but I would say it's not a very much prerequisite to know the machine learning first and then go to the deep learning. You can directly jump into the deep learning, provided you have a good interest level as well as a good uh, understanding of the maths and code behind that.
All right. So Prasanna has a question for you. He's asking how Amex uses AI and deep learning.
I think everywhere, every decision making, we have millions of transactions happens on a daily basis, and every transaction go through those machine learning algorithms, whether it's a risk predicting the fraud, credit, for various other kind of marketing related solution. We use machine learning. In fact, my team is responsible for across the globe machine learning and AI for the MX side of it. And the way and every decision making we do is just going through these algorithms only. So we do not make any decisions without machine learning and all. So you could say that everywhere, everywhere.
All right, quite interesting. The other question is, could you please let us know few real-time use cases where deep learning was applied successfully?
Even myself has applied many problems on the deep learning side of it. In fact, previously I was in InfoEdge group, which is Naukri, Shiksha, Jeevansathi, 19acres.com. We build a real-time recommendation engine out there, and with essentially not only just a collaborative filtering kind of algorithms, but at the same time we use content-based recommendation engines. We used to extract features of the text. We used to on the top they were sitting on a network model at the end, which are making using of these features and recommending set of jobs to the job seekers, and they are all real time. And even if you update your profile just now, those your recommendation get updated, and backend all kind of algorithms were working out there, and that's myself has built it. That's why I could say that. But there are n number of applications of the deep learning. Let's say Google Translator is the one you could see. The moment you speak, the moment you type, it can really give you this kind of solutions. So there are a lot of application the real time where the deep learning can be applied. Even we ourselves are going to use the deep learning algorithms for MX problem for our own use cases in real time side.
All right, Manish. The next question is by Pawan. He's saying, can we use deep learning for generating test data set by feeding production data set to deep learning model?
Yeah, I think I've covered this one. GAN, which is your general adversarial networks. You could use this particular networks to synthesize your data, and which can really help you to really make a better model. And the way it works is basically work on the critic based on the real samples, and there's something called generator. They generate through random samples, and then they try to mimic like a real sample. I think there's interesting work by Ian Goodfellow, uh, and his PhD is based on that only, and a pretty interesting work. And I think this is one of the most cited paper in the recent past with because synthesizing data synthesis is one of the most popular term in the deep learning today.
Okay, Manish. The next question is by Satender. He's asking which type of deep learning model to use for audio analysis and speaker recognition.
It's LSTM only. I think I mentioned it. RNN and LSTM is a no-brainer for uh, time series and speech and text kind of a data, audio type of data.
All right. The next question, I think the second last question will be, what is the activation for binary classification and multi-class classification?
So I think activation it depends upon the problem set, but majority of the time, let's say for binary classification at the end we use sigmoid, and for multi-class we use softmax.
Okay. I guess now it should be the last question. There are many more, but looking at the time constraint, so let's have the last question, Manish. So it is how to apply deep learning in the field of medical insurance in bracket medical record summarization.
There's so many works is happening on the healthcare and especially the medical one out there. I would again suggest go to the healthcare workshop or the papers on the KDD. This time there enough work on the medical side. They're called electronic health records, EHR data. There are a lot of work is happening. Even I was mentioning about the patient next visit, for what disease that some person would visit next, when the need readmission would happen for this one, and people are using all sort of deep learning algorithms for various kind of health related one problem. So I think it's a so much work happening on the deep learning side, on the healthcare side. I think if you just Google it or go to that particular links, I think you may see lot of papers on those lines.
All right, so I guess we are coming to an end of this session. So thank you so much, Manish, for this amazing presentation. I'm sure attendees have learned something new to execute in their projects. And I would also like to tell you one more thing, that NASSCOM Product Conclave is approaching on 25th and 26th of October in Bangalore. Please register by visiting our website under event section, nasscom.in/events. And see you on Thursday on the session on GTM by Raghavendra of Yellow Messenger. Thank you so much, Manish. So see you anytime soon again to collaborate and learn
Okay.
something new.
Okay. Thank you so much.
Thank you. Thank you, everyone. Take care, all of you. Bye. Take care.
Okay, bye.